This video demonstrates a generic simulation solutions heat exchanger simulator, highlighting its purpose, functionality, and potential teaching objectives. This simulator includes both a DCS view, which represents what an operator would see in a control room, as well as a virtual reality outside operator view, which serves as a visual model and provides a sense of reality for trainees. These two windows communicate with one another such that a change in one window is correctly reflected on the other. The following is a countercurrent shell and tube heat exchanger with water and diatherm as the working fluids. 85° Fahrenheit water enters the shell side of the system at a specified flow rate. The water leaves the heat exchanger at a design rate of 105° Fahrenheit. The heating fluid, diatherm, which enters the tubes of the system at 140° Fahrenheit, is used to achieve this heat transfer. The diatherm leaves the system at a cooler temperature of 120° Fahrenheit. The water into the system is on straight flow control, but the temperature of the water leaving the exchanger is the primary controller in a cascade loop. This temperature is controlled by the flow of diatherm, which serves as a secondary controller. It is important to note that numerous possible instructor-introduced faults exist within the simulator. These include pumps failing and valves failing open or closed. The virtual reality window presents an outside view of the heat exchanger system. Trainees can operate pumps, control valves, and read indicators. Here, you can see the water flow control valve. If I go to the DCS and make a set point change, and I run it, you'll notice that the valve begins to open. Now, if I place the controller in manual, and I lower the output on the DCS, we will see that the valve begins to shut. If I leave the controller in manual and go to the virtual reality outside operator, the student is able to manually open the control valve from the field. They could also shut the control valve from the field, as would be the scenario in this case. So aside from the DCS and the outside operator, each simulator is accompanied by a comprehensive laboratory exercise booklet, which provides exercises that allow instructors and trainees to work in conjunction using our trademarked INSTO methodology. INSTO stands for Identification, Normal Operations, Startup and Shutdown, Troubleshooting and Upsets, and Optimization and Operating Strategies. We believe that before trainees can troubleshoot or optimize a system, they must understand where the system equipment and controls are located, as well as how they function. In addition, they must be aware of how the system operates under normal, startup, and shutdown conditions. One exercise that allows instructors to assess their trainees' mindset are what-if questions. Instructors provide a scenario to the trainees in which either a flow rate, pressure, or temperature changes within the system. Then, trainees are asked to determine what these effects will be. For example, one exercise includes assessing the effects of an increase to the inlet water flow rate. These exercises are executed via a minds-on, hands-on training strategy. Trainees will first predict how they think a change will affect the entire system. Once predictions are recorded, the trainees will each make the move on their simulators and report what they have seen. If this report matches the prediction, the discussion will be brief. However, if there are discrepancies between the report and the prediction, a more in-depth discussion will be had. So now if we go back to the DCS, we can test this what-if exercise. So if I put it into design conditions, and we increase the flow rate of water going in, we notice that initially we see that the outlet temperature takes a hit. Because this temperature is cascade controlled, the diatherm flow increases to get back to the design temperature. Because the whole system got colder with the increase of water, the outlet diatherm temperature also initially drops. Trainees can view these changes from the DCS screen or more in depth in the Advanced Trend window. So here we're going to look specifically at the What If Group trend page. As you can see, any change I made is tracked based on its time and its effect on other variables. So now that we have assessed this what if exercise, let's see the results. So each laboratory exercise booklet includes recaps to these types of exercises, and this provides trainees a visual of what is going on in the system. So here we can see that an increase in the flow rate of water causes a decrease and then increase in the cold diatherm temperature, no change to the water flow inlet temperature, decrease then increase to the outlet water temperature, increase to the flow rate of diatherm, and no change to its temperature inlet. So this provides an example of a type of exercise that would be common in a laboratory exercise booklet. Simulation Solutions believes that the implementation of training simulators is extremely important, and that the corresponding comprehensive laboratory exercise booklets provide the necessary foundation to allow trainees to become safer, more comfortable, competent, and knowledgeable.